guys, today we're going to have continuity of functions. Can you trace the broken lines without lifting your pen or without passing through the same broken lines more than once? If you need more time to decipher this question, you can press pause. Continuity of function is like tracing the broken lines without lifting your pen and without passing through each portion of the line more than once. Now, let's take a look at the three graphs presented on the screen. Which do you think demonstrate or exhibits continuity of functions? Again, you can press pause if you need more time. In these three graphs, only letter A exhibits continuity of function. If we trace the graph, let's have letter A. Take note that we can trace the graph in A without lifting our pen and passing each portion once. While here in option B, if we trace this graph, we need to lift our pen in order to trace the other parts of the graph. The same with option C, wherein we need to lift also our pen in order to trace the other portion of the graph. So hence, only the graph illustrated A shows continuity of functions. Now let's describe continuity of functions formally. A function is said to be continuous at the number A if all the following conditions are satisfied. First, f of A exists. Second, the limit of f of x as x approaches A exists, and the limit of f of x as x approaches A is equal to f of A. If any one or more of the given conditions fail, the function is said to be discontinuous at a number. Let's work on example number 1. Determine whether f of x equals x squared minus 2x minus 3 is continuous at x equals 1. We now show that the function satisfies all the three conditions. So we show that f of 1 exists by evaluating the given function at x equal to 1. So we will have 1 squared minus 2 times 1 minus 3. Simplifying that, we will have negative 4. Therefore, f of 1 exists. Now let's show whether the given function satisfies the second condition, wherein the limit of f of x as x approaches to A exists. Okay. We show that the limit of x squared minus 2x minus 3 as x approaches to 1 from the left is equal to the limit of x squared minus 2x minus 3 as x approaches to 1 from the right. Now we evaluate x equals, or we evaluate the given function at x equals 1, so we will have 1 squared minus 2 times 1 minus 3. We also evaluate the given function at x equals 1, so we can see that they are both equal to negative 4. So hence we can say that the limit of x squared minus 2x minus 3 as x approaches 1 is equal to negative 4. Hence the limit x squared minus 2x minus 3 as x approaches to 1 exists. We can see that the given function satisfies the second condition. Now, what about the third condition? We are asked to show that the limit of x squared minus 2x minus 3 as x approaches to 1 is equal to f of 1. Now we can see that this is equal to negative 4 and f of 1 is also equal to negative 4. Then we can conclude that the function satisfies the third condition. So with this, we can confidently say that f of x is continuous at x equals 1. We use graphical method to confirm our conclusion or our answer that the function is continuous at x equals 1. Okay, so using GeoGebra or Desmos, we can have this graph and we can plot the point at which we have x equals 1. So here we have x equals 1. Now if we will trace the function, we can see that we can pass through this point without lifting our pen. Hence, we can say that f of x is continuous at this given number, x equals 3. Is this clear? Now let's move on to the second example. Determine whether f of x equals 2x squared plus 11x plus 5 all over x plus 5 is continuous at x equals 0, and the second one is x equals negative 5. We show first that, or we determine first that the function is continuous at x equals 0 by using the three-step method. Okay, we evaluate f of 0. So we will have 2 times 0 squared plus 11 times 0 plus 5 all over 0 plus 5. Simplifying this, we will arrive at 5 over 5, which is equal to 1. Hence, we can say that f of 0 exists. It satisfies the first condition. Now let's have the second condition. Okay, the limit, we have to determine whether the limit of f of x as x approaches to a exists. So we have to get 2x squared plus 11x plus 5 all over x plus 5 as x approaches to 0 from the left is equal to the limit of 2x squared plus 11x plus 5 all over x plus 5 as x approaches to 0 from the right. So we need to show that these two are equal. So evaluating this, we will have 2 times 0 plus 11 times 0 plus 5. We will have 0 plus 5, and we need to show it's equal to this. We will have 0 plus 5 in the denominator. So simplifying this, we will have 5 over 5, which is on the other side is we have also 5 over 5. They are both equal to 1. So hence we can say that the limit of 2x squared plus 11x plus 5 all over x plus 5 as x approaches to 0 is equal to 1. So therefore, this limit exists. Okay, So we can say that it satisfies the given condition, the second condition in particular. So we can conclude that this limit exists. Now let's take a look at condition number 3. We show that the limit of 2x squared plus 11x plus 5 all over x plus 5 as x approaches to 0 is equal to f of 0. Okay, let's take a look. This is equal to 1 and f of 0 is equal to 1 also. They are equal. Hence, we can conclude that f of x is continuous at x equals 0. We support our answer that it's continuous. Okay, this is the point on the graph where x is equal to 0. Okay, now if we trace this graph, we can pass through this point continuously without lifting our pen. Now let's try whether the function is continuous at x equals -5. We again use the three-step method. We evaluate the given function at x equal to -5. So 2 times -5 plus 11 times -5 plus 5 all over -5 plus 5. Okay, to simplify this, this will be 2 times 25 minus 55 plus 5 all over 0. Now in the numerator, we also have 0. So this is an indeterminate form. Therefore, f of -5 does not exist. Now, since it does not satisfy the first condition, we can already conclude that say that f of x is discontinuous at x equal to -5. In other words, we can also say that f of x is not continuous at x equals -5. Now let's support our answer using a graph. Okay, so graphically we can show 2x squared plus 11x plus 5 all over x plus 5 using this line. Now since we cannot use -5 for x, this point will be represented using an unshaded dot or a hole. So if we will trace this graph, we will be interrupted by this hole in order to continue tracing the graph. Therefore, we can say that f of x is not continuous at x equal to -5. Now let's take a look at example number 3. Investigate the continuity of the function f of x, which is defined by the two function x squared minus 1 where x is less than 2 and x plus 2 where x is greater than or equal to 2. Again, we use the three-step test. So we determine whether f of a exists. Now since we will evaluate the given function at x equals 2, we will use this function since at this function we can get a condition that x equals 2. So if we will have f of 2, we will evaluate x plus 2 at x equals 2. So simplifying that, we will have 4. So f of 2 exists since we have a real number. Now what about if we will check whether this function satisfies the second condition? We have to prove that the limit of f of x as x approaches to 2 from the left, okay, is equal to the limit of f of x as x approaches 2 from the right. So we evaluate in the limit of f of x as x approaches to 2 from the left. We will evaluate, okay, the limit of x squared minus 1 as x approaches 2 from the left, whereas the limit of f of x as x approaches to 2 from the right would be the limit of x plus 2 as x approaches to 2 from the right. Now evaluating the two limits, we will have 2 squared minus 1. On the other side, we have 2 plus 2. So we will have 4 minus 1 on the other side. Okay, on the other side, we will have 4. Now, we simplify, then we conclude since 3 is not equal to 4, then the limit of f of x as x approaches 2 does not exist. Okay, since we have arrived at two different values. So with this, we can say that f of x is not continuous at x equals 2. Now we support our answer using a graphical method. Okay, so if we trace, okay, the graph, okay, we will be interrupted here when we reach this point. There is an open hole. Then in order to proceed to the other part of the function, we have to jump in order to trace this line. So from here, we can say that f of x is really not continuous at x equals 2. Okay, so that's it. Now let's have example number 4. Investigate the continuity of the function f of x equals to the absolute value of x minus 3, where x is not equal to 3, and the constant function 2, where x is equal to 3. Okay. From here, we again prove or show that this function satisfies the three conditions, so that we can say that this function is continuous at x equals 3. So we shall use, for f of 3, we shall use this function, because at this function we can see that x is equal to 3. So f of 3 is 2, therefore f of 3 exists. Now, we evaluate the limit of f of x as x approaches to 3 from the left, equal to the limit of f of x as x approaches to 3 from the right. Then we will have 3, absolute value of 3 minus 3, equal to the absolute value of 3 minus 3. Is this really equal to each other? Okay, we will have 0 equals 0. Okay, we were able to get that the limit of f of x as x approaches to 3 equal to 0. So the limit of f of x as x approaches to 3 exists. Okay, this shows that the function satisfies the second condition. So what about the third condition? Okay, we show that the limit of f of x as x approaches to 3 is equal to f of 3. Now we get the value of the limit of f of x as x approaches to 3. We have 0. However, f of 3 is equal to 2. Therefore, they are not equal. So we can conclude that f of x is not continuous, okay, not continuous at x equals 3. Okay, we support our answer with the graphical method. Okay, so take a look. Since in the absolute value of x minus 3, x is not equal to 3, this should be an open hole or an unshaded dot. So if we will trace this, then we will be interrupted by this hole before proceeding to the other part. Then to trace this, we have to jump. Okay, from this, we can say that f of x is discontinuous at x equals 3. Now let's proceed to continuity of a function on an interval. Okay, a function f of x is said to be continuous on an interval if it is continuous at every point on the interval. Equivalently, if we were able to draw the entire graph of the function on an interval without lifting our tracing pen or without being interrupted by a hole in the middle of the graph, then we can conclude that the function is continuous on that interval. So it's just an implication that this time we are going to have more than one number, but the definition of continuity is still the same. Okay, so what if we have a one-sided continuity? Okay, there are two cases under one-sided continuity. Okay, the first one is a function f of x is said to be continuous from the left at x equals a if f of a is equal to the limit of f of x as x approaches a from the left. Whereas the second condition is a function is said to be continuous from the right at x equals a if f of a is equal to the limit of f of x as x approaches to a from the right. Okay, now this leads us to the definition of continuity at a closed interval. So a function whose domain includes the closed interval from a to b is said to be continuous on the closed interval from a to b if and only if it is continuous on the open interval from a to b as well as it is continuous from the right at a and continuous from the left at b. So we try the first or the fifth example. Investigate the continuity of the function f of x is equal to negative x squared plus 2x minus 1 at the following intervals. We have a from negative 1 to 1, b from negative infinity to 0, c from 0 to positive infinity, and d from the closed interval, okay, the closed interval from 2 to 3. Okay, now we apply graphical method in determining whether the given function is continuous on these intervals. Okay, first we have from -1 to +1. Okay, we plot first those points. Okay, since we have an open interval, the endpoints -1 and +1 are not included to or not to be considered, okay, as part of this. So we evaluate whether the function is continuous, okay, from the left side of +1. So that means we will trace the function from this point, okay, up to 1. Okay, then we also trace, or by the way, we see that the graph is continuous from the left of +1. Now let's check if the function is continuous also from the right of +1. So let's trace. So from the left of or from the right of -1, we can see that we can completely trace the function without lifting our pen. So therefore, we can say that f of x is continuous at the open interval -1 until +1. Okay, now well, this time we have from -infinity to 0. So we have 0. Here is the point where x is equal to 0. Now we trace, okay, from the left of 0, from -infinity to 0. We can clearly see that we can trace the graph without lifting from the left side of 0. Therefore, we can say that f of x is continuous on the interval from -infinity to 0. What about the third interval from 0 to +infinity? Again, we plot again the point having x equals 0. Then we have from 0 to +infinity, we trace that from 0 to +infinity. As you can see, we can trace the graph without lifting our pen. We can trace the graph continuously without lifting our pen. So that means that f of x is continuous on the interval, okay, from 0 to +infinity. Now what about if we have the closed interval 2, 3? We plot these points wherein we have 2, 3, okay. So we check whether the graph is continuous from the right of 2, okay. So here we trace right of 2, that includes here, okay. Then we trace again from this function from the left of 3, okay. So we can see that we can trace the graph continuously from the right of 2 and from the left of 3 without lifting our pen. So therefore, we can say that f of x is continuous on the interval from 2 to 3. Now let's have example number 6. Investigate the continuity of f of x equal to the square root of 4x minus x squared on the interval from negative 2 to positive 2. So here is negative 2, then positive 2. So we graph. Now, from the left of positive 2, we can trace that. We can trace the graph continuously without lifting our pen until we reach positive 2. Now, let's see if we can trace the graph without lifting our pen from the right of negative 2. Now, let's have this. Okay, we trace the graph from the right of negative 2. We can see that we can trace the graph completely without lifting our pen continuously. So therefore, we can say that f of x is continuous, okay, on the closed interval from negative 2 to positive 2. As you can see, we have been discussing continuity using different examples, and some of these are not continuous, or in other words, they exhibit discontinuity at a number or at an interval. Okay, so this can be classified into 3 types of discontinuity. First, we have the removable discontinuity. Second is the jump discontinuity. Then the last one is the asymptotic or the infinite discontinuity. Okay, so let's define each one. Okay, removable discontinuity occurs when there is a hole in the graph of the function. As the name implies, we can remove this discontinuity by redefining the function at the point of discontinuity. Whereas the jump discontinuity occurs when the graph of the function stops at one point and seems to jump to another point. In a jump discontinuity, the left-hand and the right-hand limits exist but are not equal. Okay, so literally speaking, when we trace the graph of the function and then there is a point where we'll lift our pen, then we can see that this is a jump discontinuity. Okay, we lift our pen in order to proceed to another part of the graph. Okay, whereas the asymptotic or infinite discontinuity occurs when at least one of the two limits is infinite. Now consider f of x equals 2x squared plus 11x plus 5 all over x plus 5. A while ago, we were able to determine that this function is discontinuous at x equals to negative 5. Okay, so this time we determine what kind of discontinuity this function have. Okay, so as you can see, using graphical method, we would be able to have this kind of graph in which x equals to negative 5 is not allowed because this function will have a denominator of negative 5. Okay, so graphically, we can trace this completely. However, we need to be interrupted by a hole or an shaded dot on this portion. Now, if we will evaluate the limit of 2x squared plus 11x plus 5 all over x plus 5 as x approaches to negative 5, remember that this function is a rational function. So we need to determine whether this is in the lowest term already. So we factor out the limit of 2x squared plus 11x can be factored as 2x plus 1 times x plus 5. Okay, as you can see, we can cancel the denominator x plus 5. So simply, we will be evaluating 2x plus 1 as x approaches to negative 5. Now, take note here, 2x plus 1 is already a continuous function as x approaches to negative 5. So this implies that we can remove the discontinuity of this function. Thus, we redefine the function at the point where the function is discontinuous. So we will have a removable discontinuity in this case. Now, in order to redefine the function, we have to have the constant function negative 9, where x is equal to negative 5. Hence, we can already say that f of x is continuous at any point on the graph. Okay, so that makes sense why this kind of discontinuity is called removable discontinuity. Okay, so let's have another example. Let's determine the type of discontinuity exhibited in f of x equals x squared minus 1 where x is less than 2 and x plus 2 where x is greater than 2. Now, using its graph, we would be able to see that if we trace the graph, okay, we will be interrupted by this hole, then jump to another point in order to trace the other part of the graph. So in this case, we will have a jump discontinuity. We cannot remove the discontinuity in this kind of function. Now let's have example number 8. Determine the type of discontinuity exhibited in f of x equals 1 over x squared. Now graphically, we can see that as the value of x approaches to 0, the value of f of x approaches to positive infinity. So by definition, we can conclude already that this graph is discontinuous, and kind of discontinuity would be asymptotic or infinite discontinuity. Okay, by definition, at least one of the limits is equal to infinity. Okay. Now let's have a recap of our lesson for today. There are two main concepts that we have learned. We have continuity of functions, which literally means tracing the graph of the function without lifting our pen. We can also use the three-step method in order to determine whether a function is continuous at a number or not. With this, we need to satisfy three conditions, which are f of a exists, the limit of f of x as x approaches to a exists, and that the limit of f of x as x approaches a is equal to f of a. When these conditions are satisfied, then we can conclude that the given function is continuous. Whereas if any one or more of the given conditions were not satisfied, then we can say that the function is discontinuous. So when this occurs, there are three possibilities. Okay, the first one is the removable discontinuity. Okay, by the name itself, it implies that we can remove the discontinuity of the given function by redefining the function at the points of discontinuity. Second is the jump discontinuity, in which when we trace the graph, we lift our pen in order to trace the other parts of the graph. Lastly, we have the asymptotic or the infinite discontinuity, in which it occurs when one of the limits is equal to infinity. So thank you for being with me in today's lesson. Hope to see you again in our succeeding lesson. Good day.